In this video, I will discuss the general chemistry lab for determining an equilibrium constant. And so the first thing you want to do, and this is something that you should probably do before getting to class, is actually calculating out all the dilutions you will need to do. And so that will be this right here. So we'll be using this M1V1 equals M2V2 here. And so calculating out all these dilutions before actually getting to the lab will help make things go a lot smoother and a lot quicker. And so just kind of going through the lab procedure and so forth and calculating all the dilutions you have to do and then you can essentially write down all the volumes you have to mix together and you don't have to think about it too much in the lab. And so what we will be doing in this lab is actually using Beer's law to find the concentrations of the concentration of our product so that we can actually calculate the equilibrium constant K. And so Beer's law is this. So absorbance equals K, which is this sort of conversion factor here, times C, which is our concentration. If you look online, you'll probably find, instead of K, you'll find this epsilon B here. And so that's just what K equals, where epsilon is something called the extinction coefficient, and B is just the path length. But we'll be keeping the path length constant, and we'll be keeping the uh, wavelength here at which we are measuring in the spectrophotometer constant. And so this extinction coefficient is dependent on the wavelength here. But since we're keeping those constant, we can just think of K as a constant, as an equivalence constant here between our absorbance and our concentration here. So we're using the wavelength of 450 because that is where the absorbance is highest. And so if you look at this graph here, if we go down here, that goes to about 450 nanometers right there. And so it's usually best practice to use where the absorbance is the highest. And so we'll be using Beer's law for that. And we'll also be using Le Chatelier's principle, which was from the previous lab. And so in this, we are looking at our iron 3 plus and our thiocyanate here. And so what we will be doing is having the concentration of the iron 3 plus be much greater than the concentration of the thiocyanate. And so what that will do is it'll essentially push all of this to this side so that we end up removing all of that. And so we end up with this. And since we know how much SCN is, since we know how much of the thiocyanate we put in, and we know that all of it is used up, we will know the concentration of this right here. And so we will know the concentration of it, and we'll know the absorbance from the spectrophotometer. And so we can use that to actually calculate our equilibrium constant. So in the first part of the experiment, we'll be doing what you see in this table here. And so we'll be adding in right here. So this is our sort of excess of the iron 3 plus here in the form of the iron nitrate here. And then our diluted potassium thiocyanate right here, we'll be adding that in. And so getting the absorbances for these. And so we can then plot those on a graph and find the slope for it. All right, so then in the next part of it, we'll actually be looking at the equilibrium. And so in this, we will be using no longer using the excess iron nitrate here. So we'll be using equal concentrations of the iron nitrate and the potassium thiocyanate. The iron nitrate, so I have these colored. So in this first part here, we're looking at 1 milliliter of this 0.0025 molar iron nitrate. Then in the second part, we are putting 2 milliliters of that in, and then we will be adjusting the volumes of the potassium thiocyanate we put in there. And then this is just to make sure that we have this sort of steady concentration of the nitrate right there. And we'll be finding the absorbance for each of these. And then what we will be doing is looking at the regression in order to find the K, so the K in Beer's law here. And so we'll be using this regression here, which is the sort of simple regression where we are sort of forcing the y-intercept to be at 0. So the idea is that we're saying that if there's nothing in there, if there's none of the iron 3 thiocyanate, that the absorbance then should be 0. And so that's what we mean when we're saying we're essentially forcing the y-intercept to be 0. And so I have here, this is just some numbers I came up with off the top of my head, so don't think of these as what you'll actually be using in the lab, but this is just an illustration of how to actually do this regression calculation. And so we see here, so we see in this formula up here, we have this A sub I and C sub I. And so that's just telling us that we're going from I equals 1 up to this big N here, which will be sort of the highest number. And so we have C sub 1 here. So the C sub I at I equals 1 is right there. Then we add the C sub 2, and then the C sub 3, where the 3 is our big N there. Then same for the absorbances here. And so when we calculate the K, so this is the lowercase k in Beer's law. In the numerator up here, we're adding together the product of the absorbance times the concentration there for I equals 1. So that's why I have that in green there to sort of correspond to the 1. Then up here it's the absorbance here for C sub, or over here C sub 2, and then the concentration over here at C sub 2. And then right here is the absorbance at A sub 3, and then the concentration at C sub 3. And then down here is just the C sub 1 squared. So C sub 1 squared plus C sub 2 squared plus C sub 3 squared. And so we see when we do this calculation, which I have right here, we end up with our lowercase k here in Beer's law actually being equal to 9.6 times 10 to the third, and that is inverse molarity right here. And so we end up with this molarity to the -1. And so then we will use what we've done above to actually calculate the equilibrium constant K. And so we'll actually be doing this for each one of these right here. So there are quite a bit of calculations in this lab here, but they're all kind of the same thing. And I believe in the lab it actually asks you just to show a single calculation, so a single sort of representative calculation. So this is going off of my sort of made up data up above. And so remember up here, so if we're looking kind of right here, we're adding in this first part 1 milliliter of each of them. So I'm kind of looking at it like that. So we're adding 1 milliliter of our Fe3 plus, and then 1 milliliter of our thiocyanate here. Then up here you see that we're adding 5 milliliters of this, so 1 plus 1 plus 5 gives us 7 milliliters. So we find our concentration for the Fe3 plus and SCN minus, and so that's the sort of initial concentration in our ice table. So we want to find what that is after we've mixed everything together. So we have to do this dilution here. So we get our initial concentration of the reactants. And then we want to find the concentration of the product using our Beer's law. So remember, that's A equals Kc. So our Beer's law is our absorbance equals our K times C. And so that will give us a C equals A over K. And so using that right here, we can calculate the concentration that we will get of our product right there. And so then we can put that into an ice table like this. So we have our initial right here. So we're putting the initial concentration of our iron and thiocyanate there. We have 0 for our complex ion right there. And so then we take the initial and subtract off this right here because that's how much product we're forming. So we do that in both of these. We are adding that much product. So after we subtract that off, we get these for our reactant concentrations at equilibrium, and then this is our product concentration at equilibrium. And so then we put that into our mathematical expression of the K here, of the equilibrium constant. So we have our product on top, and then we can square the reactant on the bottom because our iron 3 plus and our thiocyanate will be equal here. If they were not equal, you wouldn't be able to just square them. You'd have to put those as 2 different concentrations on the bottom. But here we used equal volumes at equal concentrations so we can square them. And so then you calculate this, and what you end up with is this right here. And so that will be our equilibrium constant for that. And so we should find that the equilibrium constant is the same in all of these. And you'll actually have to calculate with one last calculation that you'll have to do in this lab is actually calculating how far off the equilibrium constant is from sort of a control equilibrium constant. So looking at the sort of error on that. But anyway, those are sort of the calculations that we have to do on this lab. This lab is, as you can see, quite heavy on the calculations here, so just be prepared for that. Like I said, one thing that'll help is if you do these dilutions before actually getting to class. So making sure you have all the dilutions you need, so when you get to lab, you just already know what volumes of everything you need to be mixing together and what concentrations everything are. So that is sort of my advice to you before actually getting to this lab. But anyway, I hope you found this video helpful, and I will see you later.